how does the monitor display yellow? On the screen of this TV set, each pixel is made up of 3 colors: red, green, and blue. Gray is like this, and cyan is like this. If we change the ratio of red, green, and blue, we can change the color. This 3x3 console is our color changer. Through this slider, let's try to change the number on the screen so that we can see the results of slider adjustment in real time. For example, in this configuration, the picture becomes green, and by the same token, we can try to change the picture to red. Now, let's try to adjust this picture to black and white. In fact, this console is a matrix. A matrix looks like a pile of digits. What exactly do these digits do to the image? Matrix is a tool for manipulating vectors. If we want to understand matrix, we first need to understand vector. For computer, a vector is an ordered set of numbers. Our high school math teacher told us that a vector is such an arrow. The starting point is the origin, and the end point is a point in this coordinate system. You can think of it as a data or as a geometric form. The RGB color value we just played can also be regarded as a vector. It can be pure with 3 sequential values: 66, 187, 181. But if we define a coordinate system, we can also mark it in the coordinate system. If we take red as the x-axis, green as the y-axis, and blue as the z-axis, we draw a color space. It is at this point in space, for the color value of each pixel in the photo, you can find the corresponding point in the space. Now, we have an understanding of the vector. Then, I'm going to introduce you to the matrix. The thing operates vector. The matrix is everywhere. It's all around us. Morpheus explained to Neo. Let's start with the neural network equation that I talked about in earlier episodes. In this new structure, C1 equals x1 times w1 plus x2 times w2 plus b1, and Z2 equals x1 times w3 plus x2 times w4 plus b2. We can take w out and put it on one side, put x1 and x2 on the other side, then we'll get an equation with a matrix. At this point, the input x1 and x2 are whole. It is a vector x with 2 digits, and the output z1 and z2 is a vector z with 2 digits. These 4 coefficients are a matrix of 2 times 2. I usually write it down as a capital and bold letter W, which can be further simplified to z equals w times x. To restore a matrix with a familiar set of equations, we need to make x1 correspond to the first column of the matrix, x2 to the second column of the matrix, multiply them, and add them together. Come on, let's familiarize ourselves with this operation. This is a matrix operation of 2 times 2. I can click the box and drag to adjust the value in the 4 matrices so that the output value are consistent with the target values. It's easy and even boring, right? Let's watch a more vivid image to understand what just happened. First of all, I put the input vector 2, 1 in the coordinate system, and the process can be divided into 2 steps. Find the basic vector and multiply the coefficient. Basis vector is the basic tool for us to describe and categorize vector space. By default, it is the unit vector 1, 0 and 0, 1 on the xy axis, and 2, 1 can be seen as the coefficient of these 2 base coordinates. It means that it will first walk 2 units on the horizontal axis and 1 unit on the vertical axis. The addition of the vectors is 2, 1. This process can also be expressed as follows. It is also equivalent to this matrix, which can be seen as a combination of 2 vectors. The first column is the basis vector of the abscissa, and the second column is the basic vector of the ordinate, according to the operation rules we just mentioned. The result is 2, 1. Changing the matrix means changing the basic vector, that is, changing the space. For example, when the matrix is 3, 2, 1, 4, the basis vector becomes 3, 1 and 2, 4. The unit grids become such a diamond lattice. The original 2, 1 becomes 3, 1 of 2 units plus 2, 4 of 1 unit, and the result will be 8, 6. Let's switch to another point. Under the action of this deformation matrix, -2 and -4 becomes -14 and -18. Other points are similar. This time, we find that too many vector arrows will make it troublesome. We can drop the handle and the head of arrow, leaving only the terminal point. That's what a matrix does to change the coordinate system by changing the basis vector. So that the vector that are supposed to own it are moved to a new position. Now, I'm going to change the matrix so that this orange solid circle can be moved into a cyan hollow circle. I can click on the orange dot on the left, and the formula indicates the position change of this point. It's troublesome to drag a little bit like this. The safest way is to take out your paper and pen and try to solve the equations. Select 2 points and get 2 sets of data for the input x1, x2, and the target t1 and t2. After inputting 3 minus 2, we get -41, -14. Input 6, 5, get 35 and 62. Let's first look at W1 and W2. The equations about W1 and W2 can be listed according to the set of this point. W1 times 3 plus W2 times -2 equals -41. W1 times 6 plus W2 times 5 equals 35. In these 2 equations, there are only 2 unknown variables, and we can easily solve the values of these 2 weights. By the same token, we can list the equations about W3 and W4. We are moving in the right direction. Now, the 2 datasets can barely coincide. In order to clean the customers, we need all the points to coincide with the target position. Let's add a little more difficulty. In addition to mapping points in a 2-dimensional plane to another 2-dimensional plane, a matrix can also map points in a two-dimensional plane to a three-dimensional space. For example, this is a 3 times 2 matrix. According to what I just said, it builds a space with the basis vectors 1, 0, 0 and 0, 1, 1, then go 5 times in the opposite direction of 1, 0, 0, double in the direction of 0, 1, 1, then it comes to this corresponding point. Similarly, in this way, every point's location can be found in three-dimensional space. Now, let's challenge a more difficult problem. Okay, now we can go back to the filter matrix. Here, we treat the color of each pixel as a vector. Adding such a filter matrix is equivalent to recalculating every values in the vector. For example, when m is 0, 0, 0, 1, 1, 1, and 0, 0, 0, according to the calculation rules I have just explained, in the new pixels, r prime equals 0, b prime equals 0, only green ones left. If the value of 3 column values are the same, then the new RGB values are the same, then there is no difference among red, green, and blue, and the whole image becomes black, white, and gray. We also demonstrate this operation in the color space. You will find that our transformation matrix allows these colors to collectively move to another location in the color space. So let's turn this picture into black and white and see how the colors are arranged in the space. This is the multiplication of matrices and vectors, which seems to be concise and elegant representation of linear equations. It is more convenient for us to imagine the changes in space. Of course, it means more than that. For a neural network, the way it is written as a multiplication of matrix and vectors is mainly because it calculates faster. Let's take the simple and single lay perception that recognizes number as an example. To calculate the output value of a picture, our computer needs to calculate 784 multiplications and then add them up. However, if we write it as a vector dot product, only this one line of the code is needed. It means doing double processing for all x at the same time. Let me directly execute this code in this window. According to my computing power of my laptop, how long does it take to complete these two operations? This program will output the time. It is worth mentioning on my iPhone, the gap between these two is about 2.1 milliseconds. But what the neural network often needs to recognize is not this kind of low-pixel matters. For example, when performing the face recognition operation, the input data is likely to be high-definition imagery of thousands times thousands. In other words, when training the model, what the computer needs to do is the dot product of dozens of millions times dozens of million. Again, let's experience the time difference between these two different writing methods. The reason for this is that the traditional loop algorithm processes the input data in turn. Only when the previous operation is completed, the next one will be processed, while today's computers have optimized for parallel computing. In other words, it can simultaneously operate on multiple data inputs. There are many examples of these parallel computing tasks. This includes the graphic rendering of the video game. The advanced graphic cards you buy to play games are surprisingly effective in training machine learning models. Matrix is one of the tools of linear algebra. Linear algebra is not that scary. If you are interested, you can learn more about it in my video program, The Nature of Linear Algebra. Okay, this is the end of the knowledge of matrix in this lesson. Thanks for your patience to watch me out.